a few words very briefly about Vincent Miller. He is professor in ethics of technology at the Faculty of Industrial Engineering and Innovation Sciences at Eindhoven University of Technology since 2019, I think. He's also still, and for several years now, a university academic fellow at the University of Leeds. And another strong tie of Vincent's to the UK is his Turing Fellowship at the Turing Institute in London. But before that, he has been for 20 plus years a professor at the Anatolia College in Thessaloniki in Greece. So he speaks fluent Greek. And he's also has been Stanley J. Seeger Fellow at Princeton University and James Martin Research Fellow at the University of Oxford. So a number of stations, but the most extensive of which was Thessaloniki. His doctorate, by the way, is of 1999. It was still in Germany and still in German at the University of Hamburg on Realismus und Referenz. So that was still more philosophy of language. And from there, he moved gradually towards the philosophy of AI. He was, I think, a great student of Hilary Putnam. So some of his achievements, he has been and still is organizer of the conference series on the philosophy and theory of AI, PTAI in short. Just to name some of his projects, he's key expert in the International Alliance for Human-Centric AI, IAAI, which does consulting for the European Union on the coordination of AI policy. That's a real policy job. He's also PI on a Horizon 2020 EU project about inclusive robotics for a better society. And he's an expert on the Global Partnership on AI, just to name a few. And just to name a few of his publications. So here's a word cloud with from his website with some of the keywords of his publications you see in the upper right. So lots of ethics, computer, cognitive AI. So you know what to expect. So he has a monograph forthcoming with Oxford University Press on Can Machines Think? Fundamental Problems of Artificial Intelligence. And also, I think still forthcoming with OUP is the Oxford Handbook of the Philosophy of AI, of which Vincent is the editor. And his, as far as I can see, most cited paper is with Nick Bostrom on future progress in artificial intelligence, a survey of expert opinion. I suspect that we will hear about a little bit about the content of this paper in today's talk. That's just a guess. And he was the editor and translator of Hilary Putnam's Von einem realistischen Standpunkt already in 1993. He must have been incredibly young back then. And he has altogether 17 edited books and 48 papers. And unlike most German philosophers, his first monograph is still to come. And just to end on a fun note, that's also quite seasonal. Well, in order to try to collect the information on your speaker, you consult Google. So you enter the Google search string Vincent Müller Eindhoven, because I know Vincent is there. And one of the top results was this one. That's Vincent Müller. He's also at Eindhoven almost as long as Vincent Müller is, but his job is kind of different. And I'm really hopeful that this soccer Vincent Müller will just do as good a job as being a goalkeeper as Vincent Müller does in terms of being a philosopher of AI. Okay, let this be my introductory presentation. I'll stop sharing my screen and hand over to Vincent himself. I'll stop sharing.
Okay, thanks a lot. Yes, I have yet to meet the other Vincent Müller. I did get a note from the head of my department saying, "Oh, Vincent, I see you have a little additional job. You might need to declare it to the university that you're also working for PSV Eindhoven." Now, so sadly, I'm not. It would be fun. I should try to see whether I can meet him. So, can you see my slide? Slides? Yeah. Okay. Good. So, thanks a lot, Hayu, for that extensive introduction. One detail is obviously I didn't write my PhD with Hilary Putnam, but on. So the supervisor was Wolfgang Kühne. And yes, I have done quite a lot of sort of computing and AI things, including just working in computing as a student and later on. And to some extent, what I'm doing now is sort of a program of getting the philosophy of AI into the mainstream of philosophy. So I've been doing philosophy of computing and AI for quite a long time, probably 15 years or so. And at the meetings, you would see the usual suspects, and everybody would be sort of frustrated that this is a great subject and nobody else gives a damn. And obviously that has changed now. And so we're hoping to boost this development and make sure that AI becomes a standard sort of issue in philosophy as well, and not just outside of the field. Now, good. So I will talk about the following things. I'll talk a little bit about what AI is and what it will be doing. What are the assumptions that are standardly made in this area, and in particular, about the question whether more speed and more data gives us AI. I'll find out whether there are some assumptions there which I think do exist, and I will discuss those assumptions, summarize that in a little summary on what I think the relationship between AI, computing, and intelligence is. So this is really fairly general. I will gloss over lots of details, which the experts will be annoyed about, but I'm happy to talk about those in the Q&A. So here's a video that I wanted to share with you. I think in order to do this, I need to stop sharing this and then start sharing the other things. So let me try that. So I'll share this screen. Now I need to find the guy. Yes. So this is the fun part of the lecture, which is that not my part. So here is a physics professor explaining something about dominoes, which is directly relevant to our talk today on the future of AI.
Everybody knows about playing with dominoes, but what you may not know is that a domino can knock over another domino, which is about 1.5 times larger. So what I have here is a chain of dominoes. Each one is 1.5 times larger than the previous one. And the smallest domino is about 5 millimeters high and 1 millimeter thick. And I will carefully place it. And there are 13 dominoes. And the largest domino, it weighs about 100 pounds and is more than 1 meter tall. Ready? Boom. That was 13 dominoes. If I had 29 dominoes, the last domino would be as tall as the Empire State Building.
So that last bit is what I wanted to get your attention to. So if you had 29 dominoes, 29 of these little steps of 1.5 times the size, so that's the step in this case, right? Then you would reach the Empire State Building from this tiny bit that he started off with, which I think is surprising. And I hope you find that surprising too. So I'll get back to my, presentation. Okay, and now this is off. Good. I think you can hear me, right? If not, hi, somebody has to shout. Good. So what's the relevance of the story? The story with the dominoes will become clear in a second or in a couple of minutes. So what I want to explain here is, first of all, a little bit about what types of AI there are. Well, that is, what types of AI there are from a theoretical standpoint. If you would look into an AI textbook, you would not find these terms here. So what is it that people think what AI is? What kind of thing is it? Not how do we do it, not sorting or some technology that we're using in the area. So in a classical distinction that was popularized at any rate by John Searle, there is strong and weak AI. So strong AI in that understanding is generally intelligent AI that has everything that human intelligence also has. So it can mean what it says, it has will, it will have responsibility, and so on. It has fully cognitive states like we do, fully in that sense, right? Weak AI is an AI which doesn't have these states, but provides a model for these states, for natural cognition. So you can see that in both of these, the assumption is that AI is somehow very intimately connected with natural cognition, which is not obvious to an AI person at all. So this is a philosopher's view on AI. So that's why I have the third version here, which is technical AI, where basically AI is a system for solving problems, intelligently solving problems. Complex problems, typically problems that have to do with higher cognition in humans, so things like perception, language processing, planning, and so on. So typically people don't think so much about processes like moving or sort of more fundamental kinds of things, but that is, I think, changing. That is not the same, by the way, I should mention that for the insiders. It's technical AI is not the same as alien AI. So alien AI is the idea that you have an AI which is fully intelligent in some way, but in a different way from the human way. Thus alien. Okay, so again, for the non-experts, AI is different from robotics. So that's the second column there. Robotics deals with devices that have sensors and actuators, of physical devices that exercise force on the environment. Okay, they could move. They have a gripper. They have wheels. I don't know. There could be an airplane or something that moves and exercises force. And AI may or may not do that. Right? It may just sit inside a computer and do its computation, come up with some kind of result. Of course, there's physics involved there, but no forces used on the outset. So there are no so-called, the robotics is called actuators. And robotics typically, I think that's now changing slowly, but typically does not use AI because it has mostly pre-planned activity. And the last piece of little disentanglement of the notions here is machine learning. So machine learning has been in the news quite a lot in recent years. This is a specific technique in AI, one amongst many. It is divided in various subcategories, basically supervised, semi-supervised, and unsupervised. And the basic difference between machine learning systems and the other systems is that they're not programmed in the conventional sense that somebody sits down and says, aha, if you do this, you should do that, etc. But that they are trained on a set of data in these supervised or not so supervised ways. But in any case, they get their response to the data from the training. So the internal states of the system changes as a result of the training. And that also means that has various interesting results. One of them is that you can continue training it even after, for example, selling the device. You might continue training it, which is what happens on your phone, for example, when it starts realizing that there are similar faces or something like this. I'm not sure that that's machine learning, but anyway, that kind of thing. And the other important thing is that you don't necessarily know why the machine responds to the training set in the way that it does. So it could be that it does it for what you think are the right reasons, but it could turn out to be the wrong reasons, or reasons other than the ones that you had in mind. Okay, so that in that case, we would find patterns, but we can't explain why the system does what it does, which produces interesting difficulties, in particular in the responsibility for what the system does. Okay. This is a little side note. This is a page from a book by Ray Kurzweil, which I find is an interesting component of this discussion. When we talk about the future of AI, the question is, why do we care? Why do we care about the future of AI? Obviously, we care about the future of technologies, generally speaking, but we don't care that much about the future of, bridge engineering or even mobile phones or something, or that much. In the case of AI, this is different because it seems that the future of AI would determine what even AI even is. We don't really have a very good idea about this right now. It might determine whether AI would become something better than us. So this is why I call this a humiliation. So here in the picture, you see the human race sitting on the desk, right? And the human race writes these things, which says, only a human can do this, right? Only humans can drive cars, only humans can understand natural language and so on. You see lots of them are on the floor already. Only humans can recognize faces. Only humans can improvise jazz. And we or a lot of humans are worried by this. So we care about the future of AI more than we care about other technologies because it seems to say something about our role in the world. And one important aspect of that is quite simply that the role of humans, the Homo sapiens in the world, is largely due to the fact that we are more intelligent than the other species around. That's why we are in control, right? We are in control on planet Earth as much as one can be in control, I suppose. And that is not because we're faster or stronger or anything like that. It's because we're more intelligent. That is the reason. So if something new comes up, which threatens to be more intelligent than us, we are worried about it. So a lot of people will look at the future of AI and sort of when they hear something that the machines can't do it, they'll say, ha, good. That feels good. I feel safer now. So that's a danger, right? I will point out some difficulties in this sort of optimistic trajectories of AI, but don't be fooled by the fact that you perhaps like hearing this, right? You might like hearing it, but that is not a reason to believe it. So why is AI so successful? One diagnosis is quite simply that AI is successful because the machines on which we run the AI have changed so dramatically. So the machines that we run AI on, the computing machines, have become massively faster and have been able to produce massively more data, process massively more data. One well-known law, so-called law, which is basically a regularity that we've observed for a good number of years now, is Moore's law. So it seems that it's doubled every 2 years or sometimes 18 months, people say. So something like that. And we tend to underestimate the power of such a change. Right? So we say, okay, it doubles every 2 years. Okay, it gets faster. But what that means is the kind of thing that we don't really understand. So that's why I thought the story with the dominoes might be useful. You can see it doubles and doubles. You can see, look, this tiny domino with just, I don't know how many were there, 13 or something, a couple of steps anyway, it ends up toppling over this really thick one. And here, one way to think about it is the question, how many steps do you need to make in order to get to the moon? So imagine that you would make steps in the following way. Every step is twice as large as the previous one, right? So you have an exponential growth of the steps. Okay, let's say you start with a largish step, which is a meter. Let's say, so you go 1 meter, 2 meters, 4 meters, 8, 16, 32, etc. So you see, this is becoming fairly big, right? You make steps of 16 or 32 meters, but you'll say, okay, fine, it's fast. But how many such steps would you have to make to get to the moon? So sadly, the result is already in the slide. So you need 30 steps. So if you make 30 steps and doubling every time, you don't just get quite far, I don't know, from Munich to Rome or something like this, right? You get from Munich to the moon. And of course, if you made 31 steps, you would get into space as far away as the Earth is from the moon. That's the average distance, right? So I think it's important to realize that this is hard to realize. Okay, we aren't good at visualizing exponential growth. We can understand things get faster, right? But cars get faster over time. But the growth of speed is nowhere near at that kind of speed. This exponential growth, particularly in the later steps of it, is something that we find hard to grasp. So the importance of it is hard to grasp. The one person who has grasped it several times quite well and made good use of it was Ray Kurzweil. So I'll talk about him in a second. So here are some people who've talked about this, and Bert Dreyfus, particularly in a conference that I organized in Thessaloniki, he said, people think that we will just go on doing the same thing. We'll just do it much, much faster with more data, and then we'll do impressive things. And to some extent, of course, that is true. If you do have an exponentially faster device, you can do things that you would have only dreamt of before. So machine learning systems that we have now are a clear example of that kind of thing. Right? They have existed for 50 years plus, but their powers were just so limited because people could not imagine that we would have the computing power to do all these things. So Dreyfus said, to just say we'll go on is like saying the first monkey who climbed up the tree made progress towards the moon. So the monkey might say, look, I mean, I've been climbing here. I'm a bit slow, but okay, it works. I'm climbing up. And if I just keep climbing and maybe I accelerate my climbing, then I'll get to the moon in the end. Of course, that's not going to work. We are not using the right technique here. And so the question is, what are the assumptions that we have made when we say that more and more speed and more data will get us there? So that's basically the subject of the talk today, right? So the idea that if you get more speed and data, you go to AI. We do have more speed and data, therefore we go to AI. So that's what opponents like a nicely valid argument. So here's a little slide from the paper that was already mentioned before that I wrote with Nick Bostrom. We asked people by what time they would expect HLMI. So HLMI doesn't exist. We just invented that term. So that means HLMI, it stands for human level machine intelligence. So we defined that because we wanted a new word that people didn't have a prejudice about, right? So we invented a new one. And we said human level machine intelligence means that a machine can do pretty much all human professions. And we left it at that, pretty much, right? So maybe there are some professions where it is important to be a human, so that goes out, but pretty much that. So when would you expect that this happens? In particular, when would you expect that the probability that this happens goes over 10, over 50, or over 90%? In other words, you are sure that by that time it will have happened. So we asked lots of experts in AI and theory of AI about that. And the result is this graph. It's not an exponential graph, logarithmic graph, it's a normal graph. But you can see that it goes up quite fast in the beginning, and then it sort of flattens out. So people were expecting that this change will happen quite quickly. You can see it perhaps more easily in this version here. So the red number there is the median from these 4 groups that we asked. So the median was around 2040 for the 50% point. Okay, so they thought that 2040 would be the point where the probability goes over 50%. This is not a prediction on AI. It is a questionnaire on what people think the prediction of AI is, right? So we didn't make the prediction. We just asked people what they thought. And they came up with this relatively, let's say, optimistic result. And I think it's based on this idea that we already mentioned. So here's another way of looking at it. So this is something that occurred to me when we had discussions at FHI with Nick, and at that point with people from DeepMind who came to ask us about some things. And they said, we're now doing video games, and basically we think we're going to do video games, and then everything else will follow. And I was sort of wondering, is that really true? So the way they thought of it was that it's complexity. So if you have a simple game, so tic-tac-toe, right? It's like this 3x3 matrix, and you make crosses or knots, and you try to put a row. If you play tic-tac-toe, after a while, you probably don't play tic-tac-toe, right, with your friends, because it's boring. If you don't make any mistakes, you don't win. if nobody makes the mistakes, you don't win. He could predict pretty much what's going on. So tic-tac-toe has a relatively small number of possible moves that can occur in the game. I've read, I don't know, it's this number, 5,478. In chess, the board is bigger, 8 by 8, and the number of possible moves is bigger. It's limited because chess has rules as to how many times you can move back and forth in the same position, etc. And you can see rather different estimates. In any case, the number is so big that you can't compute it, even with the fastest computers that we have or will have, you can't compute it all the way to the end. Go is even bigger, way more complex already, 10 to the power of 170 apparently. And other games are even more complex. And so the idea is, okay, we'll just get there. We'll just make things more and more complex. And life is just a complex video game. So this may be true or it may not be true. So Toby Walsh is the guy on the left, an Australian computer scientist. He says, or has said in a talk that I attended, a faster thinking dog is still a dog. So he doesn't think that that is going to work. He's just going to be the same thing in faster. I'm personally not really convinced that that's true. I think a faster thinking dog, which I would, if I were able to think, I don't know, 10 times as fast as I do now, which isn't all that fast, I think that would make a significant difference to my cognitive capacity. Yeah, you tell me what you think. But this has changed massively. So I looked at the computing capacity between 2000 and 2017, and it has improved by the factor of 1,000. And about a year later, another 1,000. So you can see that's the point of the exponential growth. I haven't looked at the rest of it yet, but you can see this goes up and up in a dramatic way. Here's one, sorry, and this is the number for the computing capacity per dollar. Okay, so how much you have to pay in order to get the particular computer capacity. So take out $100 or something like that, what you get for that. So here is a slightly different question, namely the computing capacity per dollar actually spent. So if you spend more dollars, you also get more. This is from a little paper or note by two people from DeepMind. And they are looking at their machine learning systems and say how many days they took to train. And this is on a logarithmic scale. So it looks like it's definitely exponential growth because it's a straight line on a logarithmic scale. But it doesn't double every 2 years. It doubles every 3.5 months. So it's much, much faster. You can see this more nicely, I think, in the second slide. This is the linear scale. The linear scale looks quite weird in the beginning. If you look at it in the beginning, it looks like everything is down there at the bottom. What's going on? Actually, you see everything is pretty much at the bottom until the very end. And suddenly alpha 0 and alpha goes 0 are going up. That's the point of exponential growth, right? So it grows, it grows, it grows. For example, it doubles every 3 months, and then it goes up in a almost vertical way. No, it's not vertical. So this is the major explanation why they've been so successful, because they just had so much more computing power at their disposal. So it's more available, and they spent more money on it as well, which is an important consideration, which philosophers have completely ignored, as far as I can tell. One footnote on this. This idea of AI and faster AI is not the same as the idea of superintelligence or singularity. The idea of the singularity is that you get faster and faster AI. So this is what Chalmers, for example, calls that AI, and then AI plus and AI plus 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 and so on. And then something important happens, and that's the singularity at that point. So I have it here in a very nice quote from Irving Good in 1965. Notice in 65, he says, an ultra-intelligent machine could design even better machines. They could then unquestionably be an intelligence explosion, and the intelligence of man would be left far behind. It's curious that this point is made so seldom outside of science fiction. Okay, so never mind the sexism of man in this case, but the point is, the machines, there would be a point in his view where the machines would be doing the design of the machines, and then things would grow exponentially. So this may happen, but this would assume that you get to a point where the machines become better at doing that than the humans are. Okay, which you don't have to assume, but this is a basic assumption is in this slide here. So this is Ray Kurzweil's notorious slide where he explains the development of computing power. That's a logarithmic plot again. And he says it gets faster and faster, and it's going to reach insect brains, human brains, and at some point it's going to surpass the human brain, and then we'll get into the singularity. That's the idea. This is a very powerful, simple and powerful idea, and I think one is something we have to grapple with. What do we think about this idea? It has lots of problems, of course. One problem is there such a thing as the intelligence? So you have one dimension that you can just say, oh, this one has 16 and the other one has 27. How do we measure that? What is it? Is there really such a thing what you could sort of apply to humans, turtles, machines, anything? Can you measure it? Are you perhaps, when you're measuring, confusing what you measure with the target? What is going on? It doesn't seem to work like that. It seems that this is what the graph on the right-hand side is trying to explain, is that we have systems that are really, really good at very specific tasks. And natural cognitive systems are not like that. Natural cognitive systems are sort of okay at everything, but not really specifically good at specific tasks. So there seems to be like a space for other systems there. So it's not clear what the assumption there is, whether it's a good assumption. The classic assumption in AI is that intelligence is the same as utility maximization. So basically, what an intelligence system does is that it finds out what is the likeliest path of action that will lead to more of the thing which I think is good. Whatever that is that I have to find good. Okay, so that's from Stuart Russell's book on this matter. Nick Bostrom picked up on that kind of idea and says we define a superintelligence as any intellect that greatly exceeds the cognitive performance of humans in virtually all domains of interest. Okay, the cognitive performance with this aim. So essentially what you do is you try to figure out, look at the various choices, you look at the expected utility of these choices, that's the technical term. So what is the positive thing in these choices and how you measure that? Then you look at the probability that this expected utility will occur, right? Because of course it could be that you know that things will happen in the meantime that will prevent so and so from happening. And then you act in such a way that you maximize the probability. So for example, you don't buy a lottery ticket because the expected utility, rationally speaking, is very, very low because the probability of winning is very, very low. And that's all there is to intelligence. This leaves out an important component that I've just recently written a paper about, namely the reflection on the goals themselves. So here the idea is the system has the goals, it has a utility function, and it tries to maximize this, right? So, but humans don't just do that. Humans also think, what is important? What should I do? Should I do this or what should I aim for? Right? What is it that really matters? And so we can reflect on this. And for example, we can do ethics, right? So we can reflect on our goals and say, yes, that is not a goal that you should be pursuing. Okay, so that's assumption. That's point number one, the notion of intelligence. Obviously a very murky discussion here. Point number two, for the optimists in AI, so to speak, is that we don't need cognitive science. So the classical AI, the way Searle and other people interpreted it, was very closely connected to understanding how humans do these things. So you have two humans here who are solving cognitively complex tasks. The one on the right, Garry Kasparov, is solving a task that was for a very long time the classic task for AI, right? Playing chess. So, and one thing that people were looking at is, how do humans do this? What is it that allows them to do this, given the fact that we can't compute all the way down, because otherwise it wouldn't make sense to play chess. So there's heuristics, and we evaluate the pieces and the positions, etc. So you try to find out how that works, and then you try to interpret this. you try to put this into a machine. So the view that AI will just progress really, really quickly towards a super intelligent AI says we don't need to do any of these things. We just need to get the machine to do its job in its way, not in the way that humans do it, and solve the problem in its way. That might be a completely different way. And that seems perfectly fine. We're just solving a problem. It might turn out, and this is why I have the slide, that hard things are easy and easy things are hard. So we tend to think as humans that the guy on the right is doing something more intelligent than the guy on the left. That's Marco Reus. Sorry to my apologies to the people in Munich. So actually, it turns out that that's false. It turns out that playing football is much harder than playing chess. We thought it's easier, but because little kids can do it, but no, it is actually much, much harder. It's more dynamic. You need to look at all the interaction with the physical world and the team, and you need to make projections. And primarily, you need to move your body around the environment and so on. Very hard. Robotics is quite far away from achieving anything like that. And of course, chess is solved. So one other assumption, which is often made, even though I think it's not strictly speaking necessary, actually, if you refuse the previous one, is that cognition is computation. So what the humans do is computational. In the classic picture, this was necessary, right? Because you would say, okay, the humans solve this computational problem. We find out how that works. And then we solve the same computational problem in the same way in the machine. Now, if you say, I don't care how the humans do it, then of course you could say, well, the humans do it in some way. I'll do it in a computational way. Okay, which of course raises the question, is the computational way universal? Can you solve any kind of problem in such a way? So here, this is the classical computationalist discussion. Is natural cognition computational? This is a very long story. There seems to be pretty strong evidence that that is not the case for everything at any rate. And that particularly, it seems to be that we need some kind of bodied grounding for cognitive function. And that is the case with humans and other animals, but not with machines. Assumption number 4. Assumption is that the current technologies are basically on the right track. So we basically have the correct classical AI where we represent the world, we sense the world, we represent it, make a plan, and we carry out this plan. This is basically how it's supposed to work. We add some new things to this, for example, machine learning, but roughly this is the right kind of thing. So this is to a large extent either wishful thinking. We hope the technology we have is the right one, or it's based on a very general assumption of what intelligence is, which I've said in the beginning is dubious, right? So we don't really know that intelligence has to be of the right sort that these technologies can solve it. If intelligence really is computation, then yes, right? Computers can do it. But if it might involve other things, then we might be in for some trouble. One last point, which I think is really important and typically overlooked, is what's called technological readiness levels. This is now a popular thing in the European Commission. You have to say these things if you apply for money. This was originally developed by NASA and their space and flight programs. And they said there is a significant difference between saying, yes, in principle, I know how I could do it, and actually doing it, right? Actually having a system that works. So readiness level 1 is you have some basic principles, maybe you have a concept, that's 2. Experimental proof of concept means you have the kind of thing that does it. So imagine, let's say, imagine flight, right? So you can say, yes, I have the first thing that somehow flies. So Lilienthal or something like that, right? Could be the kind of thing, but no engine yet and so on. Yeah. Then you start validating it in a lab, validating a relevant environment, demonstrating it, have an actual prototype, complete system, and so on. So it might turn out a lot of the stuff that you thought was really easy is not that easy. So I've given a similar talk to this one, I think 4 years ago. And I said, I had a slide on autonomous cars, and I said, this is going to cause a lot of headaches, and people are are going to find out how driving is actually quite hard. And people were shouting at me, basically saying that I'm just ignorant of the huge progress of technology. But actually, driving is a lot harder than we thought. Right? So yes, under certain very neatly defined circumstances, driving is quite feasible. But the world is a very messy and complex place. And so the real environment, the operational environment, is going to cause huge trouble. And yes, autonomous driving is quite hard, and certainly autonomous driving on the level of completely autonomous driving, that's level 4, is not something that we know much about. So this is, in other words, an investigation of this notion of speed and data leads to AI. So as I said, I think it has various assumptions which are problematic, that the intelligence has this one-dimensional shape and can be measured, and so on. That seems problematic. It could be the case. It's problematic. Cognitive science isn't needed. Yes, I put 2 question marks. That's probably too much. I think cognitive science is, strictly speaking, not needed, but it might turn out that it helps us a lot in understanding the complexity of the actual task, right? But it might take us the wrong way, right? If people had continued watching birds in order to learn how to fly, they would have concluded that continue to try and make something which has flapping wings, which wasn't the way for humans, given the machinery that we did have. Computation is sufficient for cognition is very likely wrong and problematic, and perhaps not needed if you are actually thinking that you do it without cognitive science. Are the current technologies really scalable? Are they going to continue by just what my friend Anders Sandberg calls grind? So we just sort of keep going, keep grinding forward, then we will just get there in the end. Like, walking up a mountain, you just keep going most of the time. It's okay, but unless something really strange happens, suddenly you find a rock face in front of you, then you need to have some inspiration on how to tackle that kind of problem. So it might well be that these technologies are not like that. Grinding is not what we need. And there might be some limits, right? I mean, so I don't know. Airplanes, for example, have limits. You can't make them any size you like. And then maybe technological readiness level would turn out to be really hard in some cases, which I think we've seen. So generally speaking, I would suggest that the systems that we're looking at in AI aren't thinking machines. We shouldn't look at them like that. We should look at them as technical devices that are solving interesting problems. And humans aren't computers either, but we don't need that assumption. That was needed in the classical picture, but we don't. But we should remember that AI systems will change the world radically. So I think there is a tendency of people to say, that discussions like Ray Kurzweil and so on are having a very simple-minded view of intelligence. So we throw out that stuff. That's just nonsense. They don't understand what's going on. That's a mistake, I think. Ray Kurzweil has a very good point, because these systems are going to change the world radically. And the major reason is speed and data. Of course, computer scientists aren't just waiting for hardware to develop, right? I mean, they have a job to do. So there is algorithmic improvements and so on. But basically along the same trajectory that we're already on. So these things will radically change the world, and they are radically changing the world. Even in my modest lifetime, the changes are dramatic, and they seem to be, if anything, accelerating rather than getting slower. So I think we should continue thinking about these things. This is why I have this thing there, which is from a little video clip. I'm not the future, you are. I am, as was said, trying to write some things for OUP, and I am organizing a new conference, the PTAI conference, that is Philosophy and Theory of AI conference in Göteborg in Sweden. That's at the end of September. We are hoping to have a hybrid conference, that is with actual physical people in the room. And the call for papers is actually on the webpage already. It's not official yet, but I'll make it official pretty soon. So if you're interested in working on these subjects, then consider submitting papers, talking to us about these matters. Thanks for now. Okay.
Thank you, Vincent. Thank you very much. We do this on behalf of the audience who can't, well, who can do this, but we can't hear or see this.